was something like d2x mu right? This was a geodesic equation. So this tells us how a particle moves under the influence of gravity or in a curved space. Okay. The parallel transport equation was an equation for a tangent vector. Which is so these are not the same, right? You can say, okay, if you take n mu to be dx mu du, then it satisfies the corresponding equation because of a geodesic equation. And that essentially reflects the fact that along the geodesic, okay, the tangent vectors okay, which in this case is dx mu du, tangent vector is parallel transported along a geodesic. But other than this observation, these two are quite different things, right? Because this is telling us how a particle trajectory looks like, and this is telling us that if you start with an arbitrary vector n mu and parallelly transport it along a curve, this curve need not even be a geodesic, how it evolves as you move along the curve. Is this clear?
Yes, yeah, it is clear. The confusion was that why are they similar? What is the significance that they sort of
yeah,
are
so
similar?
that's because of this statement. So that's the fact that they are similar is essentially this statement that if you take the tangent vector, then they are parallel transported as you move along a geodesic. So this is a tangent vector to a geodesic, right? This will be the tangent vector to the geodesic. If you have a geodesic, then this gets parallel transported as you move along the geodesic. Are there other questions?
Yeah, so we defined the geodesic as a length extremizing curve, right? But in pseudo-Riemannian space, when the metric is not positive definite, the length element need not always be positive. So how are we making sense of the square root and the extremizing of that function?
Well, you can still think in terms of extremization that as long as it's either a space-like or time-like geodesic, right? You can start with a time-like curve, and you are only doing infinitesimal variation. So you take a time-like curve and they do an infinitesimal variation along the curve. You demand that the first variation is 0. That gives a time-like geodesic. And similarly, you can start with the space-like geodesic and do an infinitesimal variation. Space-like curve, and do an infinitesimal variation. And by demanding that equal to 0, you get the space-like geodesic.
Space-like is when the element is negative?
Pardon?
By space-like, you mean when the length element is negative?
No, length element is positive. The way we have defined it, if you remember our signature eta or a G mu nu has one negative eigenvalue and all positive eigenvalues. So for time-like curve, right, ds square is negative. ds square is negative for time-like. Curve and is positive for space-like curve. Because you do the extremization of either ds square or minus ds square, square root of ds square or square root of minus ds square, depending on whether it's time-like or space-like. But under infinitesimal variation, a time-like curve will remain time-like, and similarly, a space-like curve will remain space. Right? So you don't have to worry about this suddenly changing sign.
Okay, that's why you mentioned like extremizing rather than minimizing.
Exactly. Yeah. Okay. Any other question? Okay, so let me then start. Somehow this is taking time. Okay, so the first thing we want to do today is to complete the definition of the energy momentum tensor for the electromagnetic field. So let me write this. So energy momentum tensor for electromagnetic field. So let me recall what we have gotten so far. So you'll be working in flat space time first. Okay, then you'll do the curve space generalization. So particle trajectory follows okay, this is the usual Lorentz force law. Then electromagnetic field equation has the form eta okay, this is the current. So let me write down the expression for J. So J mu of x was sum over n integral so all of these we have seen before. So what we want to do now is to check the J mu of x is this. I have to write one more thing. The energy momentum tensor Tx mu alpha is sum over n okay, so this is the energy momentum tensor for the same part. So we have seen all of this before. Okay? And what we also verified last time was that this energy momentum tensor is conserved, but that was for neutral particles. Okay, so let me remind you again how it went. So if you take dx, the divergence of dx mu alpha. So this derivative acts on this delta function because that's the only place where the small x is hidden. Once it acts on the delta function, then we can combine this term dx and mu d tau times the derivative of the delta function, okay, and the sum over mu. Maybe I can write the sum over mu explicitly. Okay, doesn't matter here. So this I'll write what it is. So it's sum over n integral d tau n mn dxn alpha d tau n, and then dd tau n of delta 4 x minus xn of tau n. Okay, this part is identical to what we had earlier. Okay, so if we expand this out, okay, you will recover this, because when the dd tau n acts on this, you can apply on any of the xn's that are sitting inside the delta function. It's a product of 4 delta functions. So there will be 4 terms from this product. Okay, and each of these terms basically gives you dxn alpha d tau n, dxn mu d tau n times the derivative with respect to x mu of delta 4 of x minus xn. Okay, so that's how you get to this form. Is this clear? This is something that we had gotten last time. But there is one thing that fails compared to last time. If you recall, what I did last time is that we took this minus dd tau n, okay, integrated by parts, so that it became d2xn d tau n square. And then we used the free particle equation of motion to say that d2xn d tau square is 0. Okay, and that's how you establish the conservation of the energy momentum tensor for the free particles. What goes wrong here is that when you apply this dd tau, when you do this integration by parts, you get dxn alpha d tau n square, but that of course is not 0 anymore, right? It's given here. So this is what we are going to use now. Okay, we'll do the integration by parts, and then we'll apply this equation, the Lorentz-Force law. I hope this is clear. So at the end of it, we get okay, boundary terms of course vanish at tau equal to plus minus infinity. And now we are going to substitute. So this is sum over n integral d tau n. And then I substitute eta alpha nu f nu 0 times en. Sorry, let me do one more step. So I write this as en eta alpha nu f nu rho dxn rho d tau n. Okay, that's this object. Okay, that's the Lorentz-Force law. Delta 4 of x minus xn of tau n. And now what we are going to do is to rewrite this in terms of the current. So let me show what we had the expression for the current. Remember that there is an expression for the current which is given by this en dxn dun times delta 4. Okay. So using this, we can basically substitute part of the result that we got in the next slide in terms of this current JMU. Okay, so that's what we are going to do now. So I can write this now as eta alpha nu f nu rho and j rho of x. Okay, so the explicit reference to the particles is gone. We have expressed in terms of the current zero. Are there questions on this? So we are now going to one more step, okay, because we want to get rid of the current as well. And for that, we are going to use the Maxwell equation. Okay. So here we see that the current, normally we use this equation to get F in terms of the current. Okay. But now what we are going to do is to substitute for J, okay, the left-hand side of the Maxwell's equation. Okay, so that we lose all reference to the currents. So this I'll now write as minus theta alpha nu F mu rho, and for J rho I substitute theta rho sigma Okay, is this clear? So all I have done here is that I have expressed the violation of the conservation law in terms of an expression that involves only the Maxwell phase, okay, and nothing else. And now I leave it as an exercise to check that this can be written as minus okay, I'll define what this TEM beta mu is. TEM beta mu is beta this alpha to. Okay, so this is a straightforward exercise. If you just take the divergence of this, okay, and you have to do some manipulation using the Bianchi identities, right? You remember the Bianchi identity of the field strength. Okay, you have to do some manipulation from the Bianchi identities to show that the divergence of this is exactly what you have here. Okay, this expression over here. Okay. So then we have this equation. Okay. The divergence of Tx is minus the divergence of the electromagnetic energy momentum tensor. So this is what we call the electromagnetic energy momentum tensor. Okay. And so this can be summarized by saying that the divergence of Tx mu alpha plus T Em mu alpha is 0. So while the matter energy momentum tensor by itself is not conserved, the sum of the two is conserved. And this is important because, as we have seen earlier, that whatever appears on the right-hand side of the Einstein's equation must be conserved because the left-hand side has divergence, is free from divergence. So if you are trying to write Einstein's equation, you have to use the combined energy momentum tensor of the matter and electromagnetic field. Is this clear? Are there questions? So one can easily write down a covariant version of this. Okay, that basically replaces the etas by G. So let me write. So the covariant version. This is now in chord space time. So T and beta alpha. And then the Einstein's equation. Takes the form of R mu nu minus half R G mu nu equal to C times Tx mu nu. Where C is a constant, right? If you, you are supposed to evaluate C by comparing the weak coupling limit. So this is basically 8 pi times the Newton's constant. Okay, are there questions on this? And finally, let me emphasize this again. Okay, and we discussed it last time. Is that if you have any new other kind of force, those the energy momentum tensor corresponding to those also have to be included on this side. For example, if you have a nuclei as sources of gravity, right, the nuclear binding energy will also form part of the right hand side. Okay, that's not part of the electromagnetic force. Okay? So you have to introduce a strong interaction energy momentum tensor on the right hand side. Okay, and only then it will be consistent, because it's the total energy momentum tensor that is constant. Okay, so we need this relation that this has to be 0. Okay, so this is sacred. So this says that the Einstein's equation on the right hand side must include every possible source of energy momentum tensor. Is this clear? So this finishes the formulation of Einstein's equation. So what we are going to do next is to study solutions to Einstein's equation. Okay, how do we go about trying to find non-trivial solutions? So we'll start with the simplest possible case, that is static solution describing the gravitational field of a point charge. Point mass. And so here, let me describe the analogy. So analogy will be the electrostatic field of a point charge. Okay, where you have this equation. Right? So suppose you have an equation like this, and you want to find the corresponding solution for phi. So here there are various simplifications that one can do. Okay, so let me remind you how we go about solving equations like this. Okay, this is the first thing we do in electrostatics. First, we use symmetry. Use spherical symmetry. So that phi is really a function of r. Okay, it doesn't really depend on the other coordinates. Second, we can simplify life even further by solving the free equation, solving the source free equation. Away from r equal to 0, okay, which is basically that we have the and this has a solution that is phi equal to a plus b by r. Okay, it's simple to solve. Then the constant a you typically set to 0, by as we were saying that the potential goes to 0 at infinity. So a equal to 0. Okay, this is convention. And then you find b by Gauss law. Okay, which is basically that integral minus grad phi dot ds, this surface integral, is equal to q. Yeah, this is the electric field, so the integral of the electric field should be equal to q. This is the Gauss law, and this basically fixes phi finally to be of the form c over q over r. So this is so what you want to do for gravity is a generalization of this. Take the simplest possible situation where you have a point mass and you want to see what kind of field it produces. So we'll try to use spherical symmetry, and you are going to use the source free Einstein's equation first. Once you have found the solution, then we can fix the parameter by demanding that there is a source sitting at the origin. Are there questions? So our goal will be to find spherically symmetric solution. Solution to source-free Einstein equation. Which is R mu nu minus half R G mu nu equal to 0. Now we can simplify it further by multiplying by G mu nu. So if you take G mu nu times this gives you, so this becomes R, right? Because G mu nu, R mu nu is R. And this gives a minus half times G mu nu is 4, right? Because it's a trace of a identity matrix. So half times 4 times R equal to 0. So this basically tells us R equal to 0. So if R is 0, then you can substitute back in this original equation. And this tells us that R mu nu must vanish. So in absence of source, what we find is that the Ricci tensor must vanish. These are sometimes called the Ricci flat manifolds. So
Can you
we'll
please explain again how R is vanishing?
Oh, because you have this equation, right? You multiply by G mu nu. So G mu nu, R mu nu gives you R, and this gives you minus half R times 4, right?
Yeah,
So
okay.
this combination is R minus 2R, right? So that gives you R equal to 0. Is this clear?
Yeah, thank you.
Okay. So then this is the equation that we have to solve. Are there other questions? So now we're going to impose symmetry. Okay. So there are two classes of symmetries. One is time independence. And two is spherical symmetry. Now, in general relativity, one has to be a little careful about what one means by time dependence and spherical symmetry, right? Because as we have been discussing, the general coordinate transformation is part of an allowed transformation, right? And the equation should not change under general coordinate transformation. But of course, the form of the solution could change, right? You may have a solution which is time independent, and then by making an appropriate coordinate transformation, you can go to a form in which it looks like time dependent. Okay, because you can just simply change the definition of the time form. So there is a way to specify what one means by time dependent, independent, and spherical symmetry in a coordinate independent way. Okay, so there is a way to specify them using a coordinate independent way. Specify these in coordinate independent way. And this we may discuss near the end of the course. But for now, we'll take a practical approach. Okay, the practical approach to what we mean by time independence. So our definition of time independent and spherical symmetry would be the following: that we demand that there is a coordinate system T x1, x2, x3 such that ds square is invariant under the following two transformations. First, under t goes to t plus constant. Okay, then in this coordinate system, okay, this must be asymmetric. The ds square should not change under a transformation like this. And second, under this x goes to x, xi go to xi. And the second one is that t goes to t and xi goes to rij xj, where R is an orthogonal matrix. R transpose R equal to identity. Okay, so R's are constant matrices. So these are constant matrices. Satisfying this. Is this clear? So in other words, our definition of time independent and spherical symmetry will be that it is possible to find a coordinate system in which the solution is explicitly independent of time and in which the solution remains unchanged when you rotate the coordinates. Okay, and here the rotating the coordinates basically means the standard rotation. Okay, this is the way we rotate a space coordinate. But let me emphasize again that this definition is tied to a particular coordinate system. You can certainly change coordinate system in which these properties will not hold. But nevertheless, for now, we just take this as a definition of what we mean by static and spherical symmetric solution. Is this clear?
One question here.
Yes.
Yeah, how do we know that such a coordinate system will always exist? I mean, there may be some geometries where we may not be able to find this kind of a coordinate system, right?
Yeah, certainly. Because most geometries don't have either time independence or spherical symmetry. Right? So what we said is that we are trying to look for a time independent and spherical symmetric solution. And our definition of time independent and spherical symmetric solution is that those solutions must have a coordinate system. That there should be some coordinate system in which the solution is manifestly independent of time and manifestly invariant under rotation. So you'll be looking for class of solutions of this type. But certainly the claim is not that every solution of Einstein's equation can be written in this form.
So we may be looking at a very special class of geometries, right?
Exactly. Right? Just like when you look for the solution due to a point charge, right? We look for a very special kind of solutions. Time independent spherical symmetric solution, right? So you have to take it in that spirit, that it's certainly not the most general solution of Einstein's equation. Right? It's a very special kind of solution that describes the field around a point mass. Okay? But that also only in a very specific coordinate system. Is this clear? Okay. So this solution is a spatial solution, right? Certainly it's not a general. If you are trying to look for a generic solution, it's not of this type. This should this R shouldn't get confused. I don't know, maybe I should call it something else. It's certainly not has nothing to do with the Riemann tensor or Ricci tensor. Call this S. So the first task is to write down the most general time independent and spherically symmetric solution. Not yet solution, configuration, right? Then you'll have to put it in the Einstein's equation to solve it. So let me write it down and then we'll see if we have missed anything. So in the XY coordinate system, so okay, let me define first R. We define R as square root of x1 square plus x2 square plus x3 square. Okay, just like we do in flat space time. So in this case, this has no, I mean, this is not necessarily the radial distance or anything, right? Because the metric can be complicated. But this has the property that R goes to R under rotation, under xi going to Sij, xj. Right, so this is a function of the coordinates of the space coordinates, so that it's invariant under this rotational symmetry. So then the claim is that the most general spherical symmetric time independent configuration has the following structure. Where this dot basically means sum, right? X dot dx without any metric. This is just sum over I xi dxi. Okay, without using any metric or anything. So the claim is that this is the most general configuration that we can write down, which has this property that it's independent of time, right? That under t goes to t plus constant, the solution should look the same. That's the reason why nothing can depend on time, right? You can see all of these are functions of R only. And it also has spherical symmetry. And that's the reason why it doesn't depend on any of the other combinations of the coordinates x1, x2, and x3. It depends only on this particular combination, right? All of these are functions of R only, as you can see. Okay. And furthermore, we can see that these are all invariant under rotation and time translation, right? dt square obviously is invariant. dt x dot dx, dx by itself is not invariant under rotation, right? Because dx will rotate by this s, but x dot ds is. Okay, that's why I have used this x dot ds. And similarly, dx square and x dot dx square. This dx square is a standard dx1 square plus dx2 square plus dx3 square. And then x dot dx I've already defined. So the claim is that this is the most general configuration which satisfies the requirement of time translation invariance and spherical symmetry.
One question here. So,
Yes.
so I think so. Is this enough? I mean, there should be additional constraints on the functions f1, f2, f3, f4, right? Because this thing has to satisfy the Einstein field equations. So, and those
Yeah,
are
yeah.
a set of
So I'm
differential
not saying that
equations.
this is a solution here, right?
Yes.
So
But
I'm just saying that there is no question. I mean, I have not stated that this is enough, right? But this is the most general class that you can write down.
yeah, and it's not immediately obvious that, I mean, if let's say we put this in as an ansatz, I mean, will the structure of this solution remain conserved under some sort of, I mean, if we plug under evolution, time evolution?
Under evolution.
Yes. So if we
Well,
demand
we
that
put
this,
in Einstein's equation, right? I mean,
yes,
if it solves Einstein equation, then that's a solution, right? If it
okay,
doesn't solve Einstein,
yeah, but what I'm saying is that, I mean, let's say, I mean, what is so special about this form? I could have had some other kind of, let's say, x square, I mean, higher powers of x also, right? X, I
yeah,
mean,
those are
x1,
there
x2,
as part of this. These are arbitrary functions of R, right?
okay,
So higher parts of x's are certainly included in this.
okay, okay. So you mean up to here, we have only demanded symmetries, right? Nothing else.
Exactly. Nothing else.
Okay.
Right? If you can think of any other form, right, which I have not included, then we can argue that we can try to see, I mean, why those are not included, right? The claim is that there is no other form.
Okay.
That anything you can write down, right, must be of this form.
Okay. So if we restrict the symmetries that we demand, so here you have demanded, I mean, SO3 rotation under SO3. Let's say I just demand a symmetry such that the solution is symmetric about a rotation about only a particular axis. Then
Yeah, then there's of course more general choice,
okay.
right? I mean, again, we go back to the example of a point charge, right? For
Yes.
a point charge, we require spherical symmetry. But if you didn't demand spherical symmetry, then certainly the answers will be more complicated.
Okay.
Right? But from physics consideration, we expect that for a point charge, the solution should be spherical symmetry. The same intuition is working here, right? That for a point mass, there's nothing to distinguish different directions. So you expect that the whatever configuration you will get will be a spherical symmetric configuration. Right? If you had a line distribution of mass, for example, then certainly there will be less symmetry. And you have to consider more general answers for the solution. Is this clear?
Yes.
Any other question? Okay. So now what we are going to do is to try to simplify this form by making some coordinate transformations which do not destroy the time independence and spherical symmetry, right? And we will see exactly what we mean by this. So the first we want to change coordinates. Okay, we change coordinates. We change coordinate to r theta phi. Okay, and r theta phi will be defined exactly in the way we define the polar coordinates. So let me write this. So x3 is r cos theta, x1 is r sin theta cos phi, and x2 is r sin theta sin theta.
Sorry,
Then once you have introduced the so notion of spherical symmetry in the Cartesian-like coordinate system, now I can do whatever I want. Okay, because once you have gotten the metric, now I can change coordinates, and I'm going to go back to the spherical polar coordinates. Okay, using this. Okay. The reason that I didn't want to I didn't start with the spherical polar coordinates from the beginning, okay, is that the rotation is somewhat hard to realize in spherical polar coordinates, right? If you use, for example, the r theta phi coordinate, then the rotation about the z-axis is easy at just a shift of phi. Okay? But rotation about any other axis is a complicated transformation involving theta and phi. Okay? So to implement rotation, it's easier to start with the Cartesian coordinates. Okay? But of course, the Cartesian coordinates are not the most useful one for finding spherical symmetric solutions. So now that we have gotten the form of the metric, right, the general form of the metric, we're going to change coordinates to r theta phi. So in this, you can, I'll leave it as an exercise to check. Okay, the first one you already know. This will be dr square plus r square d theta square plus r square sine square theta d phi square. This one, x dot dx, we can write as half sum over I, sum over I xi dxi, so which is half d of sum over I xi square. So that's half d of r square, and that's r dr. Okay, so dx square has this expression in terms of r theta phi, and x dot dx has this expression in terms of r theta phi. So using that, I am going to write down the metric ds square in the r theta phi coordinate system. Okay, all I have done is to use the same metric that we had written down last time in the previous slide. Okay, this one, and rewrote the dx square in the polar coordinates and the x dot dx in the polar coordinates. That's what gave rise to these forms. Are there questions? Now we are going to try to simplify this further by making some additional coordinate transformation. So we define a new coordinate t prime, which is t minus phi of r. So as of now, phi r is an arbitrary function. is some arbitrary function. We'll choose it appropriately in a minute.
It's different
So
from
then-
the coordinate phi, right?
Pardon?
It's different from the
Oh,
coordinate phi.
Okay, yeah, let me change it. Yeah, this has nothing to do with the coordinate phi. We call it chi. So this chi of r is an arbitrary function. So this tells us that t is t prime plus chi of r, and dt is dt prime plus chi prime of r dr. Okay, chi prime is the derivative of chi. So then these two terms, the first two terms, these are the ones which are dt, right? So the first two terms minus f1 dt square plus f2 r dt dr takes the form minus f1 dt square is dt prime square plus 2 pi prime dt prime dr plus pi prime square dr square, and then plus f2r plus f2 r dt prime plus chi prime dr times dr. Is this clear? F3 and F4 term will leave as it is. Okay, they are not affected by this change. Now the idea is that you will try to adjust chi. Okay, chi is completely up to us to choose. We are going to try to adjust chi so as to get rid of the dt prime dr term. So what does it involve? We choose chi such that so dt prime dr the first term gives you minus 2 f1 chi prime. Okay, there's a dt prime dr has a coefficient minus 2 f1 chi prime, and here there is another dt prime dr coefficient plus f2r. So chi prime has to be chosen as f2 over 2f1, f2r over 2f1. Is this clear? So if we choose chi prime to be f2 over 2f1, then that will get rid of the dt prime dr. Again, let me just emphasize what you are doing. You are trying to bring the spherical symmetric configuration to as simple a form as we can. Okay? And the idea is that we will try to use the coordinate choice freedom, okay, to try to get rid of some of these functions. Okay, and eventually we'll see that you can parameterize the most general spherical symmetric configuration in terms of only 2 functions instead of 4 functions. Right? As of now, we have 4 functions, f1, f2, f3, and f4. Right? We'll get rid of 2 of these.
One question, what are you making vanish? The coefficient of dt prime dr.
Yes, exactly. Yeah. Coefficient of dt prime dr.
Okay.
Okay, so in terms of this new coordinate system, we'll have a dt prime square term, right? We'll have no dt prime dr term, and you have these terms as usual, right? There will be some additional terms that will get added to dr square coefficient, and yeah, to the dr square coefficient basically. So let me state again. So we choose chi prime of R to be R times F2 of R over 2F1 of R. Or more explicitly, I can write chi of R as integral with upper limit R, or lower limit doesn't matter. I can just start from anywhere of du u F2 of u of 2F1 of u. So by choosing chi to be this, we can get it of the dt prime dr. So it's a simple exercise. Let me just write this down. So exercise after this coordinate transformation. Change coordinates. ds square will be given by minus f1 of r dt prime square plus dr square these two terms in fact combine. Okay, but I have just written them down explicitly. Okay, so what I did was that I basically made this substitution, and then the dr square coefficient had already f3 and r square f4, but now you can see that some more terms will be added. Minus f1 times chi prime square will be added, right? And then there's a dr square here, right? f2r chi prime, that will also be added. Right? So that's how you get the coefficient of the dr square term is a little more complicated, right? Which is given by the sum of all these. But of course, the point now is that we can call this whatever appears inside this curly bracket, right? It's some function of r. We just declare this as a new function, right? We don't know a priori what f1, f2, f3, and f4 are anyway. Okay? So we just declare this as some new function. Okay? But the number of functions, number of unknown functions now that label the metric had gotten reduced to 3, because you have the f1, we have f3, and then whatever is the coefficient of dr square. Is this point clear? So now I'm going to make one more change of variable, and that is the following. This combination r square f3 of r, I'll call this rho square. Okay. And now this combination, so r is a function of rho. So what we can do is that I just replace r in terms of rho, okay, using this, okay, and write ds square. Let me write ds square as minus psi of rho dt prime square. What is psi of rho? Psi of rho is f1 of r. Psi of rho by definition is f1 of r. Okay, it just takes a different functional form because rho is different from r. Then the next term I'll write as plus chi of rho d rho square. Okay. So what is chi of rho? You just rewrite r in terms of rho using this. So whatever you get here, okay, as the coefficient of d rho square, okay, when expressed as a function of rho, I'm going to call it chi of. Unfortunately, the chi has appeared once before, so let me call this I. And then finally, these I can get rho square times d theta square plus sin square theta d phi square. Is this clear? So a net upshot of this is that after all this, okay, we have labeled a most general spherical symmetric time independent configuration in terms of two unknown functions of rho, psi of rho and xi of rho. Are there questions?
So in the step previous to this, how did you conclude that you only need two arbitrary functions? I missed that point.
Oh, here? Okay.
Yes, yes.
So because you have psi and xi, so let's look at this, how many arbitrary functions you have. dt square coefficient is whatever comes here, expressed in terms of rho, I'm calling it psi of rho.
Right.
Okay, that's one function. Okay. Then dr, I rewrite in terms of rho, right? The only thing that I'm using here is that the between r and the relation between r and rho involves only r, no t, theta, or phi, right?
Right.
So
Yeah.
dr square I can write as d rho square times some function of rho. Whatever that function is, I'm calling it xi of rho.
Okay. Okay.
Then r square f3 of r, I have already declared this as rho square. Right? That was the definition of rho square. So what multiplies d theta square plus sin square theta d phi square is just rho square. Okay? There's no arbitrary function involved here. Because this, by definition, is the
Okay.
new radial coordinate rho.
Okay. Okay.
So that's how I reduced the number of independent functions to just two. Right? The coefficient of the dt prime square and the coefficient of the d rho square.
Okay. Yeah. Thanks.
Okay. Any other question? So now the idea is that this is the best we can do at this stage. Okay? And we are now going to substitute this into Einstein's equation and see what we get. Right? Any further restriction on psi and xi has to now come from the Einstein's equation, because there is not much you can do to reduce the number of functions by one more. So we'll rename as t prime as t. So we are going to now substitute this into Einstein's equation. We substitute into r mu equal to 0. So this now involves some calculation. Okay, so what I'll do is that I'll write down the expressions for the various components of R in this matrix.
Sir,
Yes.
so yeah, the answers that we came up with using fixing the coordinate choice and symmetry, is this also
Yes.
valid for a non-zero cosmological constant?
Yes, it is, because you have not assumed
Yeah.
that
Okay.
you have not used Einstein's equation at all, right? So it is certainly
Okay.
valid also for non-zero cosmological constant.
Okay. Thank you.
Yeah, in fact, I mean, yeah, here you have not used Einstein's equation. Okay, what you are going to do next will require vanishing cosmological constant. So the exercise show that R let me write R, the rho component of R first. Okay, so let me again state what I have. Equation become. And here is the claim, okay, that R rho becomes an expression like this, where prime involves derivative with respect to rho. So psi double prime is basically two derivatives of psi, and so on. Similarly, R theta theta becomes this, R phi phi becomes this, and R tt becomes this. And R mu nu, when mu and nu are not equal, are all zero, so that they don't provide any new equations. So then the equations that we have to solve are the ones where each of these four terms are set equal to 0. Is this clear? Okay. So what I'm going to do is to begin at least the studying the solution, and then we'll continue next time. So let me just already point out some simplification. We see that this R rho and RTT looks similar. Okay, except that it has a psi here and a xi in the denominator. So what we can do first is that we can get rid of the second derivative. You see that as it stands, the equations involve two derivatives of psi, right? So it's a second order differential equation. But we also see that because this psi double prime appears in two different equations, By taking appropriate linear combination of these two, we can get rid of the psi double and convert this to a first order differential equation. Okay, which is always good because first order differential equations are easier to solve than second order differential equation. Okay. So what we do first is that we use the equation that psi times r rho plus xi times rtt equal to 0. Of course, r rho and rtt are themselves supposed to be 0, right? But let's just take this combination first. Okay, we said psi times r rho plus xi times rtt equal to 0. Okay. And so what do you get? These term cancels, okay, by construction. And then we can write this as, okay, I think the last term also cancels. No. Yeah, 1 over rho. So this term doesn't cancel. Let me, okay, this term cancels, I think, right? Because psi gets rid of this and xi gets rid of this. So these two terms also cancel. So you are basically only left to this last term. So this gives you minus 1 over rho times xi times psi prime plus psi prime equal to 0. Or dd rho psi times psi equal to 0. Is this clear? Okay. So the claim is that by taking this particular combination, we get dd rho of psi times psi equal to 0, which means psi times psi must be independent of rho. This means,
Sir,
yes.
I didn't get the last part. Are we putting some constraint on the equations? I mean,
No. All of these have to be set equal to 0, right? That's the Einstein's equation,
oh, yes.
right? So I'm just using one particular combination of these two equations first,
Oh, yes.
right?
Okay.
Which is psi times r rho plus xi times rtt equal to 0.
Yes, thank you.
Any other question? Okay. So let me write this again here. So we get dd rho of psi times I equal to 0. That means psi times I is equal to C1, where this is rho independent constant. So we can, I'll now show that we can actually get rid of the C1. Okay, C1 can be set equal to 1. So let me see how it goes. Okay. So let's recall that what the metric was. So you see that here we can still make, we can change coordinates. T to some A times T, where A is some constant. Okay, it still preserves time transition invariance and spherical symmetry. We are not doing anything. If you make a change of coordinates like this, then you see that under this, psi rho will go to A squared times psi rho, and xi rho will go to xi rho. So by using this kind of change of coordinate, we can set the C1 equal to 1. So by adjusting A, we can set another way of saying this is we can keep C1 if we want, okay, but effectively that sets the scale of time coordinate. Okay, if we write, for example, psi of rho equal to C1 over xi of rho here, right, then you'll get minus C1 dt square over xi of rho plus xi of rho d rho square plus rho square times this. And all you are saying is that C1 dt square I can declare as dt tilde square, right? Just use a new time coordinate and absorb that C1 inside the definition of time. Okay. So using that, we'll just from now on use C1 equal to 1, okay, or psi times I equal to 1. But once you have done that, you have to keep in mind that you have already used up the freedom of rescaling the time coordinate, and you will not be able to scale it again to set something else equal to 1, right? Because then this equation will get changed. Are there questions? So I think I'll stop here today, right? Because next equations will take a while. So the idea next time will be that we'll basically use this already. This is something you have already gotten, psi times I equal to 1. Okay, and then we'll go back to these equations again. Okay. One combination of R and R rho rho and R TT you have already used up. Okay, so that will not be of any use. So there are 3 more equations left, right? Of course, of which, in fact, these 2 are not independent, right? Because once you set R theta theta equal to 0, R phi phi will also become 0. So you essentially have one equation from R theta theta, right, and another equation that is a combination of R rho rho and R TT. We're going to use those equations to get further constant on psi and psi. Okay, after besides having the fact that psi times psi is equal to 1. And eventually we'll get a solution labeled by just one constant parameter. And that constant parameter will turn out to the mass of the object that you are trying to describe, right? It's just like we get Q over R for electrostatics, we'll get something parameterized by a single mass parameter. Okay, are there questions? Okay, if not, I'll end here today and then tomorrow we'll continue at 12. Okay, so I'll sign off.